Hi, Math 30-1. Today we're going to be going through Lesson 5 from Exponential and Log Functions. So this is going to be evaluating logs, and it's on page 191 in your workbooks. So we're going to practice evaluating logs. Okay, so far we've looked at exponential graphs, so comparing y equals 2 to the power of x and its inverse, y equals log 2 to the x. We've learned that the point 3.8 on our exponential graph indicates that 8 equals 2 to the power of 3, and the point 8.3 on a log graph indicates that 3 equals log 2 to the 8. The exponential form, 8 equals 2 to the power of 3, and the log form, 3 equals log 2 to the 8 are equivalent. So in this lesson, we're going to learn how to evaluate logs without reference to a graph or a table. So let's take a look at what Kelsey here was doing. So she was asked to evaluate log 2.8, and her work is shown. So let's look through her work and then we'll describe what's happening. So she started with log 2.8 and she made it equal to a variable. She just chose v for this one. Then from line 1 to line 2, she rewrote from log to exponential form. So at this point here, she writing in exponential form. Okay, once she had it in exponential form, she noticed that she could change the bases to be base 2. So change base. Okay, and then from there, once the bases are the same, you can drop your bases. And then here she dropped her base to solve, and she noticed that the exponent is equal to 3. And then the last thing here is she just wrote a conclusion statement, so therefore log 2.8 is equal to what the exponent was, which is 3. So this is just her final statement or final solution. So those are the steps we're going to be doing. So we're going to make our log equal to a variable, put it in exponential form, change the base, and then solve from there. So let's go through number 1. So evaluate the following logs. So first of all, log 381. So make it equal to a variable. Normally use x. And if we put it in exponential form, it becomes 3 to the power of x is 81. And we're going to work with base 3. So 81 with a base of 3 is 3 to the power of 4. And then when we drop them, we get x equal to 4. So therefore, log 381 is equal to 4. Okay, b, same thing. Make it equal to x. Exponential form is 4 to the power of x is 64. Then we're working in base 4. So 4 to the power of x is equal to 4 to the power of 3, which means x is equal to 3. So finally, log 64 is 3. Okay, for c, equal to x. In exponential form, 7 to the power of x is equal to 7 with an exponent of 1, which means that x is equal to 1. So therefore, log 7 is 1. And last one here, same thing, equal to x. So 12 to the power of x is equal to 1. So in order for anything to be equal to 1, remember that exponent needs to be 0. So 12 to the power of 0 is 1. So therefore, log 12 of 1 is 0. Okay, first example there. Okay, number 2, so same thing. Determine the value of log b of 1. So same thing, if I make it equal to x, this would be b to the power of x is equal to 1. So again, what does that exponent have to be? The exponent has to be 0. Okay, and for this one, log b equal to x. So b to the power of x is equal to b to the power of 1, which means x is equal to 1. So you'll notice that this is a little shortcut that we're going to need to remember. So whenever your argument is a 1, right, it's always going to be equal to 0. And whenever your base and your argument are the same, it's always going to be equal to 1. So just a little trick to remember. Okay, number 3 here, evaluating. So just a little bit different here. We have that coefficient 2 in the front, so I'm actually just going to ignore it for now. And let's evaluate log 8, 5, 12. So same thing. So we'll go log 8, 5, 12 equal to x, which is 8 to the power of x. 512 with a base of 8 is 8 to the power of 3, which means x is equal to 3. But that's not our final answer because we notice that it's log 8, 5, 12 times 2. So we have to go 2 times 3, which is 6. Okay, for this one here, equal to x. So 2 to the power of x is equal to 1 over 32. So 32 with a base of 2, and if I bring it up, becomes 2 to the power of negative 5, which means x is negative 5. Okay, and then for this one here, equal to x. So 5 to the power of x is equal to root 125, which we should write as a rational exponent. So it becomes 5 to the power of 3, that's the 125 part, all to the power of 1/2, that's the square root. So this is 5 to the power of x. Exponent laws, you multiply, so 5 to the power of 3 over 2, which means x is 3 over 2. Okay, good. Let's try number 4. So noticing that this time we have a base being raised to a log. So let's just work with this little log here again, evaluating. So log 5, 25 equal to x. 5 to the power of x. 25 will be 5 to the power of 2, which means x is 2. But again, that's not our final answer. That just represents the exponent. So it's 5 to the power of 2, which is 25. Okay, with b as well, same thing. If we evaluate that little log, so log 7, 49 equal to x. 7 to the power of x is 7 squared, so x is 2. Again, that's not our answer. That's just what represents the exponent. So 7 to the power of 2, which is 49. Okay, and third one here, same thing. So log 3, 27 equal to x. 3 to the power of x is 3 to the power of 3. So x is 3, which again is just the exponent. So then it's 3 all to the power of 3, which is 27. So in those 3 examples, what did you notice? So what is the value of a log a to the n? Use inverses to explain your answer. Okay, so if we take a look at all of those examples there, what do you notice? Well, we noticed that for that first one, it was 5 log 525. Our n was 25. Our answer was 25, right? This one was the same as my answer. Same thing with the next one. My n was 49. My answer was 49. My n was 27. My answer was 27. So what can we notice here? That when we have a log a of n, so when the base and the base are the same, it's just equal to that argument, which is n. So in your notes, you would say raising a base to a power and taking the log to the same base are inverse operations. Okay, so raising a base to a power, So we have a base of a to a power, and then taking a log of the same base. Those are inverse operations. So then we're just left with whatever that argument was. So determine the value of log a to the power of n. Again, if we put this in equal to x, this would be a to the power of x is equal to a to the power of n. So x would be equal to n. So therefore, log a of n is equal to n. Okay, this is a good place to just pause for a second or two and try those practice questions. So numbers 1 to 3. Okay, let's keep going here. On page 193, so try to evaluate log 5 of 50. What problem do we encounter? So we would go log 5 of 50 equal to x, and then exponential form, 5 to the power of x is equal to 50. And the problem that we encounter is we're not able to make the bases the same to solve. So we cannot make bases the same to solve. Okay, so choose the correct alternative. So if I was to guess and check, and if I was to go 5 to the power of 1, well, that's only 5. If I went 5 to the power of 2 is 25, and if we go 5 to the power of 3, it's 125. So what that means is that exponent for x has to be somewhere in between 2 and 3 for sure. And specifically, it's going to be somewhere between 2 and 2.5. So at the moment, we're not able to evaluate log 550 by converting it to exponential form. We can, however, evaluate log using a calculator by changing the base to a base that our calculator recognizes. So this is where we talk about common and natural logs. So a common log is base 10. So when that little base number is 10, so for example, if I have log 10 of 1,000, that would be called a common log. So common log, again, is base 10. So these logs are in such common use that when a base is not given, the log is understood to be base 10. So they're used so often that we actually don't even write it. So for instance, if we have log 10 of 1,000, we just write it as log 1,000, and it's implied that little base is 10. And then if you use your graphing calculator, when you press that log key, works in base 10, which is important. So in number 5 here, evaluate log 1,000 by converting it to exponential form. Okay, so we'd go log 1,000 equal to x. It's the base is that it's 10, so 10 to the power of x. 1,000 would be 10 to the power of 3, so x is 3. Okay, then if I go ahead and get my calculator and I use the log key, okay, so log of 1,000, so just like that, and enter, and then you get the same thing, which is 3. Okay, number 6. In each of the following, estimate the value to the nearest whole number without using technology, and approximate the value to the nearest hundredth using technology. So if we had this first one here, so equal to x, we would go 10 to the power of x is equal to 89. Well, and that exponent would be somewhere around 2, right? Because if I go x is 2, then we're at 100. So it's somewhere around 2 for an estimate. Okay, and then if we evaluate that, so because it's base 10, we can just go log 89 and then enter, and we get 1.95. So log 89 1.95. So again, close to that 2. Okay, and then for this one here, if we estimated it, so this would be like 10 to the power of 3, right? Which is around 1,000. So somewhere around 3 for my estimate. And then if I go on my calculator and go log of 2,000, because it's base 10, we're able to do that. So log of 2,000, we get 3.30. So again, close to that 3. So again, only if it's base 10, you're able to use your calculators like that. Okay, so common log. Natural logs, we actually don't need to talk about, so we'll just skip that. And we're working on changing the base next. Okay, so next thing we have to talk about is the change of base identity. So this just goes through explaining the formula. So I'd like to just skip right to it here. So it's right here. So if you're working in something other than base 10, it's difficult for your calculator to do it. So we have this change of base formula. So this is the way it works. So for example, if I have log b of c, we can convert them into the same base. So in this case, they chose a by dividing log a of c divided by log a of b. So this is the change of base formula here. So again, to make that base the same, this is how we go about setting it up. So let's do some practice with this here. So this one here, if I wanted to evaluate log 4 of 1,024, to convert these into the same base, so being base 10, we would just go, this would be the same as log 1,024 divided by log 4. And then again, that little base is 10, which we can use our calculators, so you just simply put it in just like that. So you go log 1,024, and you divide it by log 4. So just like that, and it works out to be 5. Okay, same thing here with number 2. So it's a log being divided by another log, so we have to do change of base for both of them. So the numerator would be log 1,024 divided by log 2. That's the numerator, divided by the denominator, which is log 4 divided by log 2. Okay, so you do the first one, so log 1,024 divided by log 2, which is 10, divided by log 4 divided by log 2, which is 2, and divide those two, which is also 5 again. Okay, number 8, evaluate to the nearest hundredth by changing the base. So again, we're just dividing them, so log argument 2021 divided by log base, log 5. So again, they're both base 10, which you just throw into your calculator, and you get 3.35. Okay, for b, same thing with that fraction. So log 1 over 1,000 for the top, divided by log 2. Okay, so log 1 divided by 1,000 divided by log 2. So negative 9.97. Okay, and then thirdly, you can keep the 3 out. So 3, and then we're going log 512 divided by log 7. So log 512 divided by log 7. Okay, and then take that value, and again, it's being multiplied by 3. So 9.62. Okay, so again, change of base is helpful in terms of evaluating when you're not able to make the bases the same. Okay, last page here. So convert the following logs to the base indicated. So I want log 6 to 16 to be base 3. So simply just going to use the change of base with a base of 3. So this will be log base of 3 of 216 divided by log 3, 6. So making those bases 3. And for this one, log 300 to a base of 5. So remember, the base there is 10, common log, but we want it to be base 5. So it'll be log 5, 300, divided by log 5, which was 10. Okay, and number 10. Find the exact values of the following here. Okay, so we can use change of base for this first one here. So this will be negative, and then log 1 over 343 for the top, divided by log 7. Okay, so log 1 divided by 343 divided by log 7. And we're just going to make that negative, which would make it positive 3. Okay, this one here is, you can use change of base again for our little exponent. So this becomes log 6 and then log 216 divided by log 6, right? And then if you evaluate that, so log 216, oops, divided by log 6, which is 3. So it's 6 to the power of 3, which is 216. And again, it's that little shortcut again, right? Okay, for C would be log square root 1 over 1024 divided by log 2. So log of the square root of 1 divided by 1024 divided by log 2, and we get negative 5. So all of these examples just using that change of base formula. Okay, and then last one here, same thing, just that extra exponent, so log 49 to the power of negative 5 divided by log 7. So log 49 to the power of negative 5 divided by log 7, and we get negative 10. Okay, so those are all of the class examples for lesson 5. So evaluating logs, I'll just let you continue working through those. Just taking a look here, what's good. Let's try the numerical, so we'll go to number 13. Okay, so the value of this expression to the nearest tenth is what? So noticing they all have different bases, so we can use that change of base, which just finished practicing. So log square root of 2 of 8 with the change of base would be log 8 divided by log root 2. And it's being added to 2. Change of base again, log 3 divided by log 9. Right, so we can just evaluate that in our calculator. So starting with that first expression, which was log 8 divided by log root 2. So 6. So this is 6 plus, and then that second part there, so log 3 divided by log 9. Log 3 divided by log 9. But it's being multiplied by 2. So it's 1. And to the nearest tenth, if we add those, 7.0. For 14, given this equation, the value of x to the nearest whole number is what? So same thing, we can use change of base, just make them equal to each other. So the expression on the left will be log x divided by log 7 is equal to the right side, which is log 60 over log 4. Okay, we can do the right side first, I guess. So if I go log 60 divided by log 4, I get that decimal, and I'm going to multiply it by log 7 to bring that log 7 over. So 2.4959, 2.49. log x is equal to 2.4959. And then if we put this in exponential form, our base is 10. So 10 to the power of 2.4959 equal to x. So let's just do that. So 10 to the power of our previous answer. And what are we rounding this to the whole number? So 313. So again, just more practice with that change of base. Okay, and then 15, very similar, so similar to 14. Okay, so that concludes lesson 5, evaluating log.